Okay, we're back. Fingers crossed that this works. Midterm review, maybe we should go through it very quickly while we can. Jumping straight to it, all logistics, Sean has had a number of posts on ED, so you can get all information about exam logistics there. The plan here is to cover the technical material that's on the midterm. And so just get a few things out of the way. Coverage, what topics are we going to cover on the midterm? Everything we've covered in lecture so far except last lecture's discussion on reliability. Okay, so the ACTs, NACs, timeouts, that's not on the midterm. Everything else is. In general, the test is only going to assume that you know the material we've covered in lecture. Okay? So everything we've covered in lecture is fair game. We're not covering, if we've not covered it in lecture or discussion section, then we're not going to cover it on the midterm. To the extent that you're using the textbook, use it to clarify for extra information or to clarify concepts for yourself. But always treat what we've said in lecture as ground truth. So if there's something where the text differs from what we've said in lecture, what we've said in lecture is what you should assume for the midterm. Okay? In general, just a rule of thumb for you to know, there's nothing on the test that involves complicated math or very lengthy calculations. So if you find yourself going down that path, you're probably on the wrong track. Okay? So use that as a hint to yourself. Other general guidelines, you should understand how things work and the solutions and algorithms we've discussed in class, but also be prepared to kind of go beyond and apply them to contexts that we may not have covered in class. So, for example, we might say, consider an AS that is not following Gao-Rexford policies for BGP. How would such and such work? Okay, you should be expecting to do that. Or we could be taking a solution we've discussed in class and applying it in a scenario or context that you haven't seen before. So like, here's a very strange topology. You get this particular sequence of failures. What would happen to distance vector? Something like that. In general, we're not testing your ability to memorize stuff we've covered. We're testing whether you've understood how things work. So again, use that as a mental picture for if you feel like we're testing how many bits were in the IP header, that was probably not the goal of the question. So use that to check whether you're on track. In general, if you see something that looks unexpected, don't let this daunt you. You have learned all the pieces, the building blocks you need to reason through a problem. Okay? So in terms of format, I believe we've released a number of midterms from the prior years, so I hope you have a pretty good sense of what the style of the exam is. We're kind of following the same style. So you can expect a set of about 25 quick questions. They vary in level of difficulty, and then we have a set of these deep dive questions on specific topics. Okay. So pace yourself accordingly. Often, not always, questions would tend to get harder as you work your way down towards the end of a question. So if you find that you're getting stuck on something, maybe move on, come back to it later. Don't spend all of your time on that last question in the quick question set. What else? Attitude, don't panic if you don't know something. We aren't expecting anyone to get 100%. None of us did. None of the TAs. I got a few wrong myself. So, and this is despite having done this many times. So just know that that's kind of the expectation. Don't panic if there's one question you aren't getting. You're probably doing just fine. Again, be confident that you have learned all the things you need to know in lecture in order to solve a problem. So there is nothing in a problem that should require you to know something that was not covered in lecture. Okay. Stay calm, as always. You can reason through it, I have no doubt. So this review, and what is the plan? We're going to try and walk through half a semester's worth of material. And so clearly I'm not going to do a deep dive on any particular thing. What I am going to do is walk through all the topics, the concepts as well as the details, highlighting what it is I expect you to know for the midterm. As always, just because I didn't cover it in this review does not mean that you don't have to know it. But if I did cover it in this review, you probably definitely should know it for the midterm. Okay? I think of the way you should use this review is kind of as a checklist. It's maybe a half an hour to go through. So when you go through it, use it as a checklist of, I was supposed to know this. Do I know it? Yes or no? Go check if you don't know it and come back to it. That's at least how I find these midterm reviews to be somewhat useful. My plan for today's lecture is I'm going to summarize, I'm going to walk through the concepts, just highlighting what you need to know. I'm not going to explain, but I also have probably, if I just keep talking to myself, I have maybe 45 minutes, at most 1 hour worth of material. So I am expecting you stop me anytime you want to go into more detail on something. Repeating a concept, repeating the point I just stated, why did you say that? Any questions you have, stop me and we can go into it. With that, any questions on midterms before we get started? Okay, so let's start. Going very bottom up, we started this class with talking about links. Right? What you should know about links are the important properties of links. The bandwidth of a link, the propagation delay of a link, this notion of the bandwidth delay product of a link and what it represents, the capacity of the link. And from those, you should be able to calculate how long it takes for packets to get delivered or for data to get delivered from one point to another. You should know the components of that delay. Transmission delay, time to get bits on the wire, propagation delay, which is the time it takes to travel across the wire, as well as queuing delay and why we encounter queuing delay. Okay? You should also just be, without doing calculations, be comfortable with ideas like, I give you more bandwidth. What happens to your delay? Or I give you a longer link that is higher propagation delay. What happens to your transfer time? What happens to application performance? Okay, so just be intuitively comfortable with these properties of a link. From links, we went to routers, and we said that routers interconnect links, or you can start to build this topology. And for the first few lectures, we talked about routers as this fairly black box concept. But then more recently, we jumped into actually what a router looks like internally. And in Rob's lecture, we went into great detail on the internals of this. This is also, as you review, one of the things I like about networking, it's also both the challenge of networking, is you kind of have to keep all the pieces in your head. Like many other subjects, when you go study them, you learn algorithm A, and then you forget all about it, and you can go learn algorithm B, and the two have nothing to do with each other. That's not the case for networking. Networking is more where you learn these pieces, but they're all going to fit together, almost like a puzzle, which is kind of fun. So test yourself on whether you understand how these pieces fit. Okay, so for example, if I took this IP router, we said the IP router forwards packets from an input port to an output port. You should now know what does that mean, forwarding a packet. So a packet comes in, it has a header and a payload. You also now know what that header looks like, right? So you can say, what happens on this line card? I have to be able to parse the packet. So remember all those version bits in the IP header. Then you can say, I have to decrement a TTL. And then you can ask yourself, why do we have a TTL? Oh, we have a TTL because of loops. Why do we have loops? Because routing is this distributed asynchronous process by which we compute forwarding tables. And so sometimes we can have loops while things are converging. That's why we have a TTL. Okay, so you get that. Then you update the checksum. Why do we have a checksum? Check that you know that. After you've done the TTL and checksum calculation, what do you do next? You do an IP lookup. What do you do the IP lookup on the destination IP address? How do you do it? You do it with longest prefix match. Why do you need longest prefix match? Because we are aggregating IP addresses. Why are we aggregating them? For scalability reasons. Okay? And so once you have that lookup, then you forward your packet out the outgoing port. Where did that forwarding table come from? That's where the control processor in this picture comes in, right? That's where we're running all of these routing algorithms. That tells you now that control plane processor, that's the control plane of this router. Everything else we talked about is the data plane. Okay? So you should be able to understand both the big picture, things like control plane, data plane, and reduce it down to how these individual pieces are actually working. So things you should know about routers. Route processors versus line cards, what's getting done at each. This notion of a control plane versus a data plane. The notion of a fast path versus a slow path and what gets processed where. And in general, know that the biggest challenge when we talk about routers is that on this data plane, we need really, really high performance. Okay? So things like options, things like fragmentation, they're stressful to the data plane. Going on with our topology. So we had links and routers. Ultimately, we said the reason we have all of this is to connect end hosts. Okay? End hosts are where we run applications. End hosts want to communicate with each other. We went from there to saying that a fundamental challenge in networking is this question of how we do routing. We then spent many lectures, Murphy's lectures, on how the basic kind of fundamentals and concepts in routing and how routing is implemented. Okay, so we talked about this notion of valid routing state. You should be very comfortable with what that means. No dead ends, no loops for any given destination. Okay. Then Murphy moved on to this notion of, okay, we have valid routing state. But what does it mean to pick good paths? And so we went into this question of link costs and computing least cost paths. Okay. So this is starting to optimize for some notion of cost metric. We talked about what those cost metrics might be. If we tell you nothing, then assume the cost metric is 1. But otherwise, typically cost metrics are things like the latency of the link. Okay. So you're optimizing for something like latency. You should know that sometimes we achieve forwarding through these things other ways like default routes and static routes. Right, so static routes was when a network operator goes in and manually configures a route that says, for this destination, go out this port. Why do they do that? Because, for example, you need to know where your destination host is connected to the router. And we said destinations don't participate in routing. So how does a router know where the destination is? Because we put in a static route. Default routes, very convenient if a certain router has only one link or network has only one link to the rest of the network. Then a default route is very convenient. It says anything that's left over, go out that link. Okay. So it's a convenient summarization. In all other cases, we run this routing algorithm or this routing protocol. Any questions? Yep? Yeah. Yeah, what was the fast path versus the slow path? This entire path on the router, where data packets come in, they get quickly processed and sent out the output port, we call that the fast path. This is usually implemented in hardware. And it'll do a very fixed set of functions like, parse the packet, update the TTL, checksum, do the IP lookup, send it out. This is all built in hardware. Hardware is very good at going very fast for very simple and limited set of functions. If you needed to do anything fancier to the packet, you would bump it up to the control plane processor, where you might process the packet for things like options, or you need to look more closely at the packet. That's one distinction between, from a performance standpoint, fast path and slow path. Typically, we implement the data plane or forwarding data packets on the fast path because we get lots of data packets. We implement routing algorithms and the routing protocols, so BGP, distance vector, link state, those run on the control processor because we aren't sending that many routing updates and control plane packets. And actually running a BGP computation or distance vector is more complex. Okay, so there's control plane versus data plane, and there's fast path versus slow path. The slow path typically runs on the control processor. This gets confusing sometimes for people. Anyone want me to repeat that? Right. Moving on. So routing algorithms within a domain. So we first started with, this fairly, I would say, simple view of graphs and how you compute routes over graphs. And we talked about 3 different approaches to routing. One, distance vector, link state, and spanning tree protocol. You should be very, very familiar with how each of these work, down to the details of, what updates get sent, how forwarding entries get computed, and so on. You should also, to the level that you can apply them in different topologies and different scenarios, all 3 of them. Okay, so let's walk through each one at a time. So distance vector, a distributed asynchronous protocol where every router is independently running this distance vector computation. The basic idea is that as a router, I'm going to tell all my neighbors about my least cost distance to every destination. And then likewise, I listen to what my neighbors tell me, and for every destination, I pick the least cost path, and then I remember the next hop or the neighbor on my way to that destination along that least cost path. Okay. You should know the components of this solution in detail, where we advertise routes, the logic or the rules for when you update your routes. So if you remember, Murphy said, if you hear about a destination you've not heard about before, put it in your table. If you hear a lower cost distance for a destination than what you currently have in your table, then update your entry. Or if you hear from your current next hop with a change in the distance, then always accept it because that next hop knows best. Okay. We also talked about periodic versus triggered updates. And then we talked about this challenge of convergence, which is when things change. Routing is very simple when there's nothing changing in the network. if you have links go up, down, link costs that change, destinations that arise, then everyone has to recompute. And while you're recomputing, you're in this state where you haven't converged. So until you come back and you converge to your least cost paths, we call that period of time convergence. Okay. So you should understand all the things that can happen when things go wrong. When routers fail, links fail, advertisements are dropped, how this can lead to the counting to infinity problem, right? And why we have this max on how far up you can count. But also understand what determines that convergence time, how we have TTL values and how we have these advertisement rules that can affect your convergence time, either make it long or make it short. So if we had nothing but this simple baseline distance vector, then the time it takes you to converge is largely dictated by how frequently you send out updates, that periodic advertisement interval, and your TTL, which is how long you hold on to a route when you've stopped hearing advertisements. Okay? And so we talked about these 3 different rules or ways by which you can reduce your convergence time and avoid loops that happen when things change. Split horizon was this notion of, if you are my next hop, I'm not going to tell you about my path to the destinations for which you are my next hop. This makes sense, right? Intuitively, if I'm going through you, why would I try and advertise that route back to you? It's like asking for a loop. Poisson reverse takes that further and says, instead of not telling your neighbor, just tell your neighbor you have a cost of infinity. And there's a very particular scenario in which Poisson reverse helps actually reduce that convergence time. And Murphy walked through it, Alex repeated it again. Walk through that again, make sure you're understanding it. And then poisoning a route is this other way of actually reducing convergence time, where when your route goes away, you immediately tell your neighbors, I have a cost of infinity. And Murphy had this very nice example where you can see how that very quickly reduces your convergence time. So to make sure you're following all of those, I think what's a very helpful way, pick a few topologies. I tend to like these 2, but pick something more complicated. Walk through scenarios where if you failed this link, what would happen? If you had split horizon, Poisson reverse, or poisoning. If you change the link cost, what would happen? If the destination went away, what would happen? And again, I'd highly encourage you to go back through Alex's notes and presentations on how these different optimizations combine. Any questions on distance vector? Okay. So link state, very different approach. Again, a seemingly simple approach. The idea here, kind of the inverse of distance vector. The idea is every router is going to get the state of all links and all destinations in the entire network. And then it's going to use that global information or that map to build this full graph of the network and compute least cost paths over that graph. And then every router is going to just store the next hop for every destination in its forwarding table. Okay, so I have the full topology, I compute the entire path, and then I just store my next hop. Again, it's simple conceptually, but things you should be aware of here is how does flooding work in link state. Right, so remember, if you go back to Murphy's lectures, if you just flood it naively, where you say, when I get a packet, I'm going to send it to all my neighbors other than the one I received it on, you can have this exponential growth in the number of messages that are going around. And so link state was doing this thing where it's remembering the highest sequence number. So it says, have I seen this message before? And if not, then I flood it, otherwise I suppress it. And that's how flooding is reasonable for link state. Also, problems you can have during convergence. It's easy to underestimate them with link state, but you still do have problems during convergence. And then in addition to knowing exactly how distance vector or exactly how link state works, be comfortable with how they differ at a high level as an approach. Right? So distance vector is this global computation where everyone's computing paths in a distributed fashion across the entire network, but you're doing it using local data based on what your neighbors told you. Link state is almost the inverse, where every router is locally computing the paths, but it's doing that using global information about the entire network that it's collected. Okay. And finally, the last approach was learning switches and STP. Why did we want this? Remember, in all the IP routing distance vector link state, we said your host, the location of your destinations was kind of statically put in at routers, so routers knew where destinations were. But what if you had this kind of plug-and-play network where you can take a host and move it from one place to another? Or if you didn't have those statically entered routes. So then learning switches and STP is a very elegant way of doing this. The basic idea is that you're going to learn routes from watching where data packets come from. So when host A tries to send a packet to B, the router that receives it says, aha, I now know where A is. And you can learn accordingly from where data packets come from. If you don't have a route, you're going to flood. And the way STP does flooding is different from link state. Right? Instead of doing what link state did, in STP, flooding works by first building this loop-free topology. Okay? And so we do that using the STP protocol. You should understand why, with learning switches, we have a different approach to flooding. Okay. Anyone remember? How is link state making flooding scalable? Yep. Yeah, so link state had sequence numbers, and it said, have I received this link state update before? It could do that because it was actually storing that link state update. Right? So it had some local state to compare to and say, yes, I have it, or no, I don't. And it could store those link state updates because it's controlled state, and there's not that much of it, so it's fine. And it was going to store that state in any case. With learning switches and STP, we're talking about flooding data packets. So there's no way a switch or a router can store all the data packets it's seen and say, aha, I've seen this data packet before. So we need a different approach, and that approach is to build this spanning tree. Okay? So be comfortable with why you need a spanning tree, how it's used in learning switches. It's used for how we flood data packets, and then also know how we actually build STP, which is building the spanning tree is very similar to how we did distance vector, with one major change, which is that we're simultaneously learning what the root of your spanning tree is, as well as your path to that root. So remember, STP was, we have one spanning tree that's rooted at a particular route that gets picked based on the ID. And so when we flood packets, we only flood it over this loop-free spanning tree. Know the pros and cons of STP versus something like distance vector and link state. STP and learning switches have this nice plug-and-play property for destinations. On the other hand, this entire idea of just disabling a certain number of links is not the most efficient way to be using your links and your bandwidth in the network, which is why learning switches and STP are typically used in fairly small networks. Any questions on intra-domain routing, or those three routing? Okay. So where are we? We went from links to routers to topologies to how we actually route over those topologies. At this point, we have all the components we need to start thinking about domains and inter-domain routing. This is a picture from one of Murphy's lectures where we said that routing within a domain, by which I mean the routing used to reach a destination within a domain, is what we call an IGP routing protocol, or interior gateway protocol. And distance vector and link state are examples of IGP protocols. But we also need some solution by which we learn about routes to destinations not in my domain, right? Destinations somewhere else. And that was the inter-domain routing problem, and our canonical protocol there is BGP, or the Border Gateway Protocol. And the inter-domain routing problem, this is referred to as EGP, or Exterior Gateway Protocol. Okay, so BGP is an example of an Exterior Gateway Protocol, or an EGP. Link state and distance vector are examples of your interior gateway protocols, or IGP. Okay. So again, intra-domain is to reach destinations within your domain. Inter-domain is so that a router within one domain knows how to reach destinations that are in a different domain. And so what was a domain? We said it was a network under administrative control. You should be very comfortable with what ASs are, this notion that you have an AS number, understand the types of ASs. So we said you can have transit versus stub ASs, depending on whether you're carrying traffic across your AS on behalf of a source and destination not in your AS, versus all you just have destinations that are within your AS, that was a stub. Tier 1 transit providers, these were the top, typically the back global ASs. They're all connected with each other. They all peer with each other. They have no provider. You have to be really deeply understand the business relationships between ASs and their implications. This notion of customer-provider relationships or peer-to-peer relationships, the fact that customers pay providers and peers do not pay each other. When we talked about inter-domain routing, we said our challenges there are very different from what we discussed in intra-domain routing. It was scalability and policy. And scalability, we said that we achieve scalability largely through hierarchical addressing. And we had this example, I'll come back to it, but hierarchical addressing was, just internalize that IP addresses are hierarchical. They're hierarchical at multiple levels. In the structure, the fact that you have a network prefix with a host suffix, they're hierarchical in how they're allocated. So we have this organization ICANN that will give a large prefix to regional registries that will hand out smaller prefixes to someone like AT&T that will hand out even smaller prefixes to a customer AS like Berkeley. And then those prefixes are assigned to different domains, and inter-domain routing works on prefixes. So an entry in your forwarding table that you compute from your inter-domain routing, that's a prefix. And then finally, we said that those prefixes can be aggregated. So this further helps scalability, but within limit, that if we have things like multi-homing in this example, here you can see where you had multi-homing required Verizon to have 2 entries rather than just 1 going to AT&T. Okay, any questions on IP addressing, autonomous systems, how they're set up? Okay. So moving on with IP addresses, we said because we have this CIDR and we have this IP address aggregation, this gives us scalability, but it complicates the IP lookup process. The IP lookup process is now not an exact match on your destination address. Instead, it's a longest prefix match. Okay, so understand longest prefix match and why this destination address matched the 4th and not the 3rd. It's because we're doing longest prefix, not maximizing the number of bits that match. We also talked about how you implement longest prefix match, so you should be comfortable with how this is actually done. We're not, we could have taken an IP address and matched it against all the prefixes in our tables. That would have been slow. So instead we build this kind of prefix tree, and we have this algorithm where you walk down the prefix tree to find the longest prefix match. And when you find the longest prefix match, then you find the next hop port that you're going to send the packet out on. Okay. So again, taking stock, what we now know, if you wanted to have an AS, you would go... what is an AS? A network that's under a single administrative control. To be an AS, you go out and get an AS number from ICANN. You then set up your AS level topology by either being a customer, provider, or peer to other ASs. You obtain a prefix, which represents all the hosts within that AS. And now the last part in the inter-domain picture that we have to think about is how do we actually establish routes between those prefixes. The big challenge here was policy. Right? We talked at length about what we mean by policy and what are typical policies. The challenge with policies is that an AS is going to want to pick paths based on policy. It has its preferences for how it wants to get to a destination prefix. But we have to allow an AS to implement those policies while preserving autonomy and privacy. Okay? An AS should be able to implement whatever policy it wants and should not have to reveal its topology or its policies, at least not explicitly, to other ASs. We said in principle you could do whatever crazy policy you want, but in practice the typical policies have to do with these business relationships and how money is exchanged. And so we had this intuitive notion of routing follows the money. Okay. We then talked at length about how you would actually implement this policy routing. And we said that in inter-domain routing or BGP, the way policy is implemented lies in how these rules around how you export routes and how you select routes or import routes to a prefix. So the setup was very much like distance vector, but now it's AS is exchanging prefixes and their path to different prefixes. Okay, but we said there are 4 big differences relative to distance vector. I'm going to see if I can actually remember them. One is that you actually advertise the entire path vector, not just the least cost. The other was that you can aggregate prefixes as you go. The third is that you don't have to export, or you don't have to advertise a route to every possible prefix. And the last one was, I forget, I believe, it's in the lecture notes, I believe it's not necessarily the highest performance path, right? That which routes you pick are not just a least cost decision, it's actually based on policy. Okay, so where does policy get implemented? It gets implemented in your choice of which routes you're importing and which ones you're exporting. Okay? And this is where GAU Rexford is actually implemented, is in this import and export policy. And so again, what was import and export? So import is when somebody advertises a route to me, which one do I actually select? And in selecting a route determines how I'm going to send traffic to that destination. Okay, and we said in selecting you will always prefer customer over a peer, over a provider. This was to make money, otherwise save it, and only pay if you have to. Exporting a route had to do with how your decision about whether you advertise a prefix or a path to your other neighbors. So when you advertise it, what that means is they will send you traffic to carry to that destination. So it's the decision about am I willing to carry that traffic. And so we said this is the export rules. If that prefix gets advertised by a customer, I'm going to export it to everyone because I'm happy to send traffic to that customer. If it's advertised to me by a pure provider, I'm only going to export it to my customer. Again, because my customer will pay me, whereas the pure provider won't. Okay. You should be very, very comfortable with the GAU-Rexford rules. Comfortable all the way from why we have them, that this notion of how money gets exchanged, how they get implemented in the form of these export and import policies, and actually how they get exchanged when we get to how BGP actually gets implemented. Yep. Right. So, and that was when we got to attributes and how you actually do attributes. Right. Oh, so we had, for example, the local preference. I'm getting to that in a minute, but okay, let's jump ahead. Hold on to that for a second, and we'll get to it when I put that up. So how is BGP implemented? So you should understand the role of border versus interior routers. Right. And you should also understand the role of eBGP versus iBGP versus IGP. Okay, so we had this picture that looked like this, where we had border routers, or routers that connect to a router in a different AS. Interior routers, all their neighbors are within the same AS. And we said border routers will have these eBGP sessions with routers in other domains, and they will also have iBGP sessions with routers, interior routers, and all routers within an AS. Many people get confused between iBGP and IGP because we think when we look at the picture, an interior router is running an IGP protocol. It's also running or participating in this iBGP session. Important to remember they're doing very different things. The IGP protocol, this is the intra-domain protocol, is establishing connectivity between all routers and hosts within that AS. The iBGP session is how an interior router knows how to reach destinations in a different domain. Okay? Yeah.
To send the data for iBGP session, will it use IGP or is it like totally different?
It uses IGP. So it's actually running TCP on top. You mean for the iBGP sessions, right?
Yeah, like to send this information about other ASs and other routers, will it use IGP?
Yes.
Will it use the same like distance vector?
Yeah. Any other questions on this picture? Yeah.
On advertisements on eBGP, are you only advertising like the prefixes you own or also prefixes you know how to get to?
Any prefix, this is where the import and export policy, and maybe this is also the earlier question. So if you take the black router there, it's receiving advertisements from some other AS for any prefix that AS is willing to carry traffic for. Okay, and then likewise, if I take what prefixes that router is advertising to the other AS, when I advertise a prefix, I'm telling that AS I'm willing to carry traffic to this destination. Okay. So how do we actually do this? Remember that route advertisements look like prefixes and attributes. Okay, so prefixes was what we just discussed. It's the destination prefixes. But we talked about 4 types of attributes that influence your route selection. One was the AS path, right? The other one was MED and IGP. So going back to policies, our high-level policies always we want to make or save money as per the GAU-Rexford rules. Once we're good with that, then what we do is try to select the best performing path, which is where AS path comes in. You pick the shortest AS path. And then when you're done with that, you try to optimize for your use of bandwidth. And that was the little dance between MED and IGP, okay, which determines whether your traffic leaves how far through your network your traffic is carried. So going back, I think, to your question now about how do I actually implement the GAU-Rexford rules. One way is in local preference, that attribute, because I assign a local preference to a particular neighbor. And that tells me whether I like routes coming from that neighbor or not when I propagate that route.
All of this is about route selection.
Yes.
And what about route export?
So there you have a policy that decides, do I advertise this route? Is this a customer route or not? Yeah. Even local pref is hard-coded in some sense. Right. An operator goes in and configures that all routes coming in on this link have a local preference of this value. And if you look through the example we had some 300 and 100, those were manually configured by your operator. Any other questions on? Okay, so things you should know how BGP works, both at the high level, this money follows, routing follows money notion and the GAU-Rexford rules. You should be able to apply it to different kinds of BGP topologies. You should also know how BGP actually implements all of this and how attributes like MED and IGP and AS-path and all interact. Okay. You should have, at least at a high level, some sense of BGP's limitations and security issues, not expecting you to know this in any great detail, but just have a sense of, for example, BGP may not pick a path that is the most optimal in terms of path length, right? Because it's prioritizing policy over performance. So at that level, you should have a sense of BGP's limitations. Any questions here before I move on? Okay, so where are we? We went kind of bottom up. We went from links to routers to topologies, intra-domain routing, inter-domain routing, which has a very different set of concerns. It has to do with how the administrative setup of the internet and how addressing is done. And so at this point, we actually have all the pieces we need for any two hosts on the internet to communicate. Okay, so you should be able to take a picture like this and step through, where did NYU get its address from? How did NYU learn about Berkeley's address? What are Verizon and AT&T actually exchanging in terms of BGP routes? What protocols are running at different points? What does a packet header look like when the link crossing Verizon to AT&T? Does it look different going on the link between AT&T and Berkeley? The answer is no. It's kind of a trick question. You update the IP header, but it's the same IP header being carried through. Okay. You should also understand which protocols are running on different links, where eBGP is running, where iBGP is running, where IGP is running, and so on. Any questions before I move on? Yeah? Right. So, and we haven't covered Ethernet. So, we've covered learning switches and STP. You should know how learning switches and STP works. Learning switches and STP are usually applied in Ethernet networks, which are an L2 network. We haven't covered Ethernet, so we're not going to expect you to know Ethernet on the exam. That said, what is an L2 network versus L3? It's really whether you're routing on IP addresses versus some kind of lower level L2 address. That's the entire difference. And when you cross so typically an L2 network would be a particular technology like Ethernet, and it would have its own technology-specific way of doing routing. And it does have the ability, if you have a multi-hop network or graph that is made up of that same L2 technology, so typically the example is Ethernet, Ethernet at L2 should be able to carry the packet from one end to another of that local network. Yeah. Yeah. In fact, Ethernet pretty much is the only one that uses it. Yeah, you should know how STP works at the algorithmic level and how learning switches enable plug and play and how that works without worrying too much about the context in which it's being placed. But you should know the trade-offs, like STP floods or it ignores certain links. And you can know that without knowing anything about Ethernet, so that you should know. Any other questions? Okay, so backing up now, we've gone kind of very bottom up to figure out how we've reviewed how all the plumbing works. Let's go now again top down, and we've talked about what gets implemented and how it gets implemented. we should not lose sight about why things were done a certain way. And we spent a lot of time on this in the first few lectures of this class. Come back to it after you've now understood how things work. So going way back to lecture number 1, we said the goal of the internet was to allow hosts to communicate across multiple networks. You now know how hosts communicate across multiple networks. You know about BGP, you know how money gets exchanged, you know about how addresses get configured, about where a network operator goes to get addresses. You know all of that. But come back to, what were some of the underlying design decisions and why did we like them? And make sure that you understand that now in the context of understanding how these different protocols work. Okay, so rolling back all the way to the very first lectures, we said that the internet reflects certain fundamental design choices on why it's built this particular way, and you should know those and you should be able to appreciate them. So there were 3 main ones I want to highlight. The decision to have a best effort service model. Right, that was this idea that I'm going to send a packet and I kind of hope it gets delivered. And we said even before that inherently a network is a shared resource. All of us as users are sharing the bandwidth and capacity of that network. And we said that there are two, that was the notion of statistical multiplexing. So be comfortable with what is statistical multiplexing and why we use it. It's much more efficient than giving every user a dedicated slice of the internet. Would have never scaled and been hugely expensive. So we like statistical multiplexing and we like sharing. We talked about 2 canonical approaches to sharing. One was this notion of reservation, that a user, an end host, is going to explicitly reserve some bandwidth along a path for some duration of time. And as opposed to best effort where I just send my packet and I hope it gets through. Okay. And we talked about 2 canonical designs for implementing each of these. One was reservations implemented via this thing we said was circuit switching, and then of course best effort was packet switching. And after those first few lectures, we've only talked about packet switching because that is what the internet does. But you should remember this notion of reservations and the trade-off relative to best effort, and also at a high level, the implications for implementing reservations in the way that circuit switching did. So remember, this was an end host. When you want to reserve bandwidth, you set up a circuit by sending this control message through the network saying, I'd like to reserve some bandwidth. And then you get an acknowledgement saying, you're good, I've reserved some bandwidth, and then you can send traffic over that circuit until you're done with it, at which point you tear it down. Okay. That was circuit switching. Understand the trade-offs between circuit switching versus packet switching and what was, the pros and cons of each approach. You're obviously not expected to know circuit switching in detail because we didn't cover it, but we covered it at enough of a level that you should be able to understand the trade-offs. Okay. Any questions on circuit versus packet switching? I know that was a while back. Yeah.
Sorry, you might have said, but both constitute statistical multiplexing, or is it only one of them?
They're both a form of sharing, so they're both a form of implement statistical multiplexing, but they do at very different granularities. Right? Circuit switching is at the granularity of a circuit. You've booked that bandwidth for the entire duration. So whether you're using it or not, that bandwidth is reserved for the duration of the reservation. Any other questions? Okay. So the second design choice that we emphasized was this notion of modularity through layering. And going back to the layers we discussed, we talked about breaking down end-to-end communication into these tasks that we then arranged or organized in these 5 layers. Okay, going from applications on the top, building on top of a reliable delivery service, on top of best effort global delivery that used best effort local delivery, all the way to actually putting bits on a wire. Okay, this was L1 to L7. And we said that once you have these layers, we introduced this notion of protocols. This is the language by which peer layers communicate. Okay, so 2 peer layers on either end. We have protocols so that they know the syntax and semantics, they know how to understand each other. Going back to that CEOs exchanging letters example. We had this figure that is important to remember, which is that at every layer, you can have multiple protocol implementations, except at the network layer where we have one universal protocol, that's IP. Things to remember, there are 3 important properties to remember in this picture. One is that we have this notion of strict layering. So every layer builds only on the functions implemented at the layer below, and it supports the API that the layer on top builds. Okay? There was a question somewhere. Yeah. Yeah, good question. Where's BGP in this picture? You got something that triggered many people with SDN. That was one of the... BGP is not here. This is the data plane layering. So this picture is capturing all the data plane protocols. Okay? So BGP is the control plane for layer 3, but it's not in this figure. No. So think about that for a bit. It's a great point to make. This protocol diagram is capturing, if I have a data packet, if I go off on the internet and I catch a data packet, these are the set of protocols and headers I could expect to see. We actually don't have a nice layered equivalent for the control plane. Okay? We have control plane protocols that support the data plane at each of these layers, but not, we don't have an equivalent diagram. There is no control plane for the application layer, for example, or control plane for TCP. It's the IP header at some level, but also making the IP header worked meant you had to have forwarding tables, which then meant you needed link state and distance vector in BGP. You mean in a physical sense? Yeah, it bits on the wire, it's the header IP. So the question is, what do we mean by IP protocol? So strictly speaking, it's the IP protocol specification, it's the IP header. But then there's a lot of supporting infrastructure that has to go into making routers know how to treat that IP header. And there you get your routing, you get your management plane and all of that. Any other questions? Other things to note in this picture, you can have multiple versions in a particular layer. So for example, we had TCP and UDP. We also have things like Ethernet or the fiber protocol at the layer 2, but we only have one IP layer. Okay. So that is the principle, having this notion of layering and having one universal IP layer. Understand why it was important, not just the fact that we have it. And why was it important and useful was that innovation was able to proceed largely in parallel. Okay. This is the benefit of having that kind of modularity. Any other questions? I know it's been a while since we talked about layering and protocols and all of that. Okay, the last thing, one of these key design choices that you have to keep in mind was the end-to-end principle. And we've come back to the end-to-end principle repeatedly when we looked at decisions that were made while designing different protocols or different headers. Okay. The idea behind the end-to-end principle is it tells us what functionality gets implemented where in the network. And so remember, we said we had these 5 layers. In terms of what layers get implemented where, we said that all 5 layers get implemented at the end host, but only layer 1 to layer 3 gets implemented in the network. We talked about why at length. Why did we do this split? Specifically, why did we not implement reliability in the network? And we attributed that decision to the end-to-end principle. We also several times have pointed out that the network layer gets implemented. It's the highest layer that gets implemented everywhere. The end-to-end principle was this argument from Dave Clark about how we reason about where to place functionality in a network. And we said the way we should think about it is, if you're thinking about implementing a function in the network, if you implement it in the network, is it completely and correctly implemented as a function? Or do you still need to implement it at the end host? And if you still need to implement it at the end host, can you get away with not implementing it in the network? Right? And something like reliability, we walked through this line of argument that said there is no scenario in which having reliable delivery in the network was going to be good enough to actually reliably transfer data between 2 applications. Right? Because worst case, your disk crashed at the receiver before you reliably transferred the data. And so if you're going to have to do this end-to-end check of on whether your data was reliably transferred, then why bother doing it in the network? But we also said sometimes you might do it as an optimization, but not for correctness. Okay? That led us to this kind of layered breakdown. Okay, so we have layers, which is how you break things down. We have protocols, which is how you communicate between layers. And then we implement them through these headers and header encapsulations. So again, going back to the CEO example of you take a letter, you put it in an envelope, you put it again in a FedEx envelope. That's the role that headers are playing in this picture. Okay, so when you look at this picture, you should be comfortable with what headers are getting added where, what headers are being removed where, and you should be able to say, given a particular layer, what headers does that layer need to understand? Or when it receives a packet, what layer will be on that packet? Okay, and when it sends it up, which headers does it actually remove before sending it up? Or which headers does it add before sending it down? So this entire process of header encapsulation and decapsulation, both what gets done, but also why it gets done. Any questions on this particular layering architecture? We then moved on to this kind of more complicated view of data packets flowing through the network. And we said we started at the application where we might have a protocol like HTTP. So we take some application data, we'll put it in an HTTP header, which is an application layer header. We would add a TCP header, add an IP header, add an Ethernet header, send it out. So when you walk through this, just test yourself, for example, by saying, okay, if I'm looking at this particular layer implementation here, the router, what headers does it have to understand? Okay. If I look at a packet over here on this link, what headers is it going to have? If I look at a packet as it's being transferred between the Ethernet to IP interface here, what headers does it have? Okay. Any questions on this one? No. Okay. So taking stock, we started looking at how we do things, and we were looking at the control plane, links, routers, topologies, domains, intra and inter-domain routing. Then we switched to why we do things a particular way. We talked best effort, layering, the end-to-end argument. There's one remaining topic, which is going back to the data plane, which is the design of IP. And I think our entire discussion of IP can be summarized by looking at this IP header. Okay, so you should know what all the fields here are in the sense of what role are they playing. So we had certain fields for parsing packets, certain fields for dealing with strange things that happen in the network, like loops or loops or corruption. We have source and destination addresses and so on. Okay. So I think just looking at this, walking through each field, reminding yourself why it's there, why we needed it, what we do with that field, but also think about our discussion about which of these fields were working out well for the internet versus not, which ones were a good design decision versus not. And a lot of that discussion about why the header looks the way it does, or what we did or did not like about the header, you can remind yourself by just doing the comparison between IPv6 and IPv4. Like, why did we get rid of checksums? Why did we get rid of fragmentation? And so on. Yeah? Yes.
So I wonder if the checksum is not in the heading, where is it?
Right. So where did the checksum go? Great question. If the end host wanted to check whether the packet was corrupted or not, we're going to have a checksum at a higher level in the TCP header when we get to it.
And another question, like at the same time, what if something was corrupted in the header itself? Let's say, like maybe the address was corrupted, or like something important was corrupted that actually changed the nature of the header.
Right.
And can like give some malicious, or like send a packet directly to some other host and like with some very like sensitive information.
Yeah, so what would have happened if, let's say the corruption, I think the worst you can think of is change some bits in the destination address. And so your packet was carried to a different destination. That destination, when it checks the checksum, it should fail.
But theoretically, you kind of like credit card information or something, and then
Fair enough. Yeah. Okay. What's the worst case you could construct?
Or this is like so impossible that we don't like care about it.
Yes, and also because those checksums often get checked in practice on your network interface card, so it's not even going to make it to a malicious. You'd have to have a lucky recipient that received it by having some bits twiddled, unfortunately on the wire. So and a totally innocent destination just lucked out and got that packet, and actually knew how to go into your operating system and fish that packet out before it got dropped and said, let me check if there's... So you'd have to have malicious code sitting on a lucky host able to tap into your operating system. So I think in practice, people don't worry. Any other questions on... Any other questions on any of the material? Go ahead.
So when we did the remediation, we said we were going to send path vectors to avoid loops. And there just seems like such an elegant solution to avoid loops. And previously we did some in my opinion, ad hoc solutions, which is poison reverse and those just seem much less elegant than just doing path vector. Why didn't we do path vector for it?
Yeah. So the question is, why didn't we do path vector for intra-domain routing? I think it's largely historical. Probably at the time people were also worried about long paths, and so then if within a domain you were advertising very long paths, this would have been a problem. I suspect if you looked now at this point in time, if we got to wipe the slate clean and redo intra-domain routing, we would say, okay, 100 hops, even that is not that many bytes. But if you go back to the time when people were designing these, they were very low bandwidth links. Right? We're talking about 10 kilobit per second links. So this idea of sending large exchanges across a network topology that we don't know about was concerning. So for scalability reasons. That is the other thing about the internet is, it's an evolving thing. You don't get to just reinvent it tomorrow. Any other questions? Okay, with that then, I think that's all I had. All the best. Good luck on the exam. I don't think it's a particularly difficult one. But...